In this lab, we will be reacting solid magnesium metal with gaseous oxygen to form solid magnesium oxide. The first step is to take two masses. These masses are integral to the experiment. It is important to zero the balance before massing. First, the mass of the two bottle caps is recorded, and second, the mass of the magnesium. Record both, and then add them together to get a total mass of the magnesium and bottle caps. Place the magnesium in one of the bottle caps and cover it with the second. Place the makeshift crucible on the ring stand and make sure that it is stable and will not fall off during the experiment. Turn on the gas, making sure the flow is not too high, and use the striker to ignite the flame. Place the Bunsen burner under the crucible and adjust the flame. It is important that the tip of the inner flame is touching the crucible, as this is the hardest part of the flame and will allow the reaction to proceed more rapidly. It should take about 10 to 15 minutes for the magnesium to oxidize. If it seems like the reaction is not progressing, then you can add a second Bunsen burner. In this lab, magnesium metal and oxygen gas, with the addition of heat, react to form magnesium oxide, MgO. Magnesium oxide is an ionic compound consisting of one Mg2+ ion and one O2- ion. Inside the crucible, diatomic O2 molecules are pulled apart and they bond with magnesium ions. This reaction occurs in nature at a slow rate, but is increased with the addition of heat. When the reaction is finished, remove the bottle cap, being careful not to burn yourself. Inside should be a powdery ash-gray substance. Mask the bottle cap with the magnesium inside and record this value. Record your mass values in a data table. The first step of the calculations is to find the mass of the oxygen in the magnesium oxide. Subtract the mass of the magnesium and the bottle cap from the final mass of the magnesium, oxygen, and bottle caps. This will give you the mass of oxygen. That it is important to note that the theoretical empirical formula for magnesium oxide is 1 mole magnesium to 1 mole oxygen, as 1 Mg2+ ion is bonded to 1 O2- ion in the molecular formula for magnesium oxide. The next step is to calculate an experimental molar ratio. To determine the number of moles of magnesium, multiply the mass of the magnesium, 0.10 grams, by 1 mole magnesium over the molar mass of magnesium, 23.4 grams. The grams of magnesium cancel, and you are left with 0.00412 moles of magnesium. The same process is used to calculate the moles of oxygen. Multiply the mass of oxygen, 0.09 grams, by 1 mole oxygen over the molar mass of oxygen, 16.0 grams. The grams of oxygen cancel, and you are left with 0.00563 moles of oxygen. Then, to calculate the molar ratio, divide each of the mole values by the smallest value. So that is dividing 0.00412 moles of magnesium by itself, 0.00412, and dividing 0.00563 moles of oxygen by 0.00412. This leaves you with an experimental mole ratio of 1 mole magnesium to 1.37 moles of oxygen. To calculate the percent uncertainty, take the absolute value of the theoretical value 1.37 and subtract the expected value 1, and divide it by the expected value of 1. Multiply this value by 100 and you're given an uncertainty value of 37%. The final step of calculations is to calculate the measured error, or the error due to the instruments used. First step is to divide the uncertainty of the electronic balance, 0.002, which is 0.001 multiplied by 2 because you subtracted 2 masses, and divide it by the mass of the magnesium. Then multiply it by 100 to get the percent uncertainty for the mass of magnesium, or 2.0%. Then divide 0.002 by 0.09, or the mass of oxygen, and multiply that by 100, which gives you the uncertainty of oxygen, or 2.2%. The total uncertainty is the two uncertainties sum, so 2.0% plus 2.2%, which gives you a total measured error of 4.2%.